Okay. Thank you very much, Vichy, for inviting me to speak here. It's been the talks I've been to so far were great pleasant. I've learned a lot. I'm sorry that I couldn't come to more actually last week, but I tried to come to as many as I can this week. Now, what I'll talk about to you today is about approximation, trying to compute things where you need to approximate. Now, why would you need to approximate, right? I mean, that's a question. Why do you need to approximate? So let's just look at, for starters, let's look at our sort of, I'm all for recycling, so I'll recycle some of Alex's lovely formulas here. So we remember the exponential families from before, and here Alex had this this term here where phi of x was the sufficient statistics and theta were some parameters. So what does this mean? So actually this here, if you look at this bracket here, this is just a function of x in some sense, right? It's a real function of x, a real number. So for each x, if you know theta, you get a real number. And of course this form here, or this shape, tells you, and in particular the phi's, they tell you what types of functions you have in there, right? So now what if you don't really know what, you might in some cases not know what your phi's are. Alex had all these examples, he had all these particular families of phi's, but in some cases you might only know that there might be some phi, or in fact maybe there is just some function here, right? And you might know, well, this function has some sort of smoothness conditions, right? So it comes from some sort of function space, and we'll talk a little bit about those function space in my lectures, so-called reproducing kernel Hilbert spaces, and then you'd still like to compute. You have some optimization problem where you actually compute maybe this whole function here. So this is the starting point. So the thing is, of course, that the space you look at is typically, it's also not going to be finite dimensional, but it's going to be infinite dimensional. So that's why you need to approximate. So that's the starting point. I just wanted to give you a bit more motivation. So I'm going to maybe repeat something which Vichy will be talking about in more detail tomorrow about the Gaussian processes and Hilbert spaces. And so if you don't understand everything today, hopefully you'll get a more direct approach from Vichy tomorrow. But by all means, ask me any questions you have. And then I'll talk about machine learning with finite elements. So the thing is here, we're talking about optimization problems. Now, if you look at optimization problems, you optimize a certain function, for example, your likelihood, or your a posteriori probabilities, and you want to compute some parameters. So if instead of you computing some parameters, you want to compute some element of some more abstract functional space, like a function from a Hilbert space, what you come into from the optimization problems, you get into the realm of variational calculus. And I'll talk a little bit about that, and a little bit about the so-called variational equations and how you approximate those. There's a lot of literature on how to do that in engineering, where people have variational problems to construct bridges, say, so in static, or to compute fluid flow. And there, again, people want to compute functions which they approximate in finite dimensional spaces. They use the so-called Galerkin method and finite elements. And this is what we'll do. But we'll face one big challenge, and that is the curse of dimensionality. And I'll talk to you about that. Our functions Typically, the functions we will look at will depend on not maybe one or two variables. They might depend on 100 variables or 1,000 variables, right? And so there, the classical Galerkin or finite element techniques used in engineering break down. So what can we use? And the answer to that are the sparse grids. And sparse grids have been invented in Russia, I think, in the 60s, around 63 or 65, I forget now. Jochen will remind me. 63, thanks, Jochen. Jochen is, by the way, our expert on sparse grids. He completed his thesis in Bonn, where most of the current work is done nowadays, and has just joined us 2 or so months ago. So, they first were invented in 1963 and reinvented in the 90s, around 1990, by Christoph Zenger in Munich, in Germany, in Bavaria. I'll also talk a little bit about some algorithms using sparse grids. So now, what I first would like to do is try to get you some feel of, the variational problems we encounter, what variational problems are, what sort of the mathematical tools behind all this are, which we'll use. So, as an example, I'll look at the regression problem. You could look at sort of any other problem if you wanted to, and I use this. Well, I guess I could use the laser pointer. It's a bit more modern technology here. Huh? So, assume that we have some data points here. So we have our data point xi and yi. So y is a real variable. So that's the dependent variable, and the predictor or the response variable, and the predictor variable is the x, which can be sort of basically at this stage from any set. We're going to specify maybe more specifically what that set will be. But basically, this could be a finite set or an infinite set. The learning problem is to find some function so that, somehow if you get a new data point x, which somehow belongs to the same, is drawn from the same distribution as your training data comes from, you get a good approximation by using this f, which you sort of found from your data point. So that's a general regression problem. So now there's two things, I think, 2 points which are maybe interesting. So first of all, a key thing is if your x is close to a data point xi, you would like that the value of your predictor is somewhat close to your, what you observe in some sense. And this relates to a smoothness. So your function f should have some sort of smoothness, right? I will model this smoothness by f being an element of a Hilbert space. I'll talk a little bit more about Hilbert spaces in a moment, and I'll ask you, who knows what a Hilbert space is. But I won't ask you now, so you anticipate my question, which will come in a few minutes. And you can try to figure out what your answer will be until then. So on the other hand, our x typically will determine only part of the variation. Right? So we don't have an interpolation problem. We don't want to find a curve which goes right through our data points, but we want to have an x which determines part of the variability of these x's. There's other factors. You might have hidden factors. You might have noise. And we want to model this data using Gaussian processes. So now let's see what that is. So what we have is that we have a model of our observation, a probabilistic model of our observation, which we somehow believe for some reason is true. And so that our y's is the sum of two things, a u, which is a function of x, and an epsilon. And epsilon is just, so this is, if we do an observation, we get a new observation at a point x, we get a value y, and that y is the sum of these two things. And epsilon is just, we assume this is a random variable which is independent of anything else we sort of observed so far. This is just basically just observation noise, right? Observation error. And then we have this other thing, this u of x, and u of x is also a random variable which depends on x. So a random variable depending on an index or a parameter x is a stochastic process. So we have some randomness in here too. And then we make some assumptions about this u of x. So here we'll assume it's Gaussian. So we assume that u of x follows a Gaussian distribution. But now remember we had this smoothness. We were talking about smoothness of our functions before. So the smoothness we now encode in a covariance matrix, in that we say that random variables to points x which are close by are correlated. So in particular, if we look at this vector of random variables at our data points x1 to xn, we assume that this is a normally distributed random vector with expectation 0. So this is actually our prior. So we assume that we have a prior on u of x, that this is expectation 0 and this covariance matrix K. And we assume that we basically know this covariance matrix at this stage. So the point I wanted to make, or I made before, is that x does not fully explain y or even u of x, right? So it's really, so at each point we have a distribution for our u of x. And also, we had, so that was the other point, that with xi close to x, because of these, the points basically which are close to each other are highly correlated, we can predict close by values. So these are a very quick, short introduction to our Gaussian process. So now if we look at the a posteriori distribution, so we assume this a priori distribution I had before, what I mentioned before. We have these data points and the data models. And so now we have I guess we can look at two things now. We can look at either the values of our u at our data points, or we look at the random variable u at the new data point x, right, which we haven't observed yet. And then we know, doing an MAP approximation, that the so linear algebra shows us that the distribution of these random variables ux of x1 to u of xn, given our data, which is this here, is normal with this expectation, and K is the matrix just containing the values. I'm sorry, here's a bracket missing. K is the matrix with our covariances plus sigma squared I, and sigma squared is the variance of our noise, inverse times K times Y, and we know the covariance matrix as well. Or we could look at the random variable u of x, and we have we have the expectation of this here and the variance here. Now the thing is, maybe let's look at one specific problem. Let's look at trying to compute this expectation here of u of x, right? That's sort of the average value of our random variable here. Now you say, okay, well, the formula is just there, right? So we have this all solved already. So why do we talk anymore about this? Well, the thing is that to solve this can be a very large and sort of complex problem. And this is how we came into it ourselves. Because if you look at very many data points y, you get huge matrices here, and you need to solve this equation here, basically. Right? So how do you solve, a linear system of equations with a very large matrix? And moreover, in very many cases, this matrix here is going to be quite dense, and we can prove that this matrix is going to be dense for very many cases. And that's a sort of a consequence of the high dimensionality of your X. So we have a difficulty here. We have maybe a million by million matrix which is dense, and we want to solve that equation. So here again, maybe we should try to approximate this. And that's what we'll do, and that's what we'll use the sparse grids for. So that's what I'll talk about to compute this here. I know this was maybe a little bit quick. So was that more or less clear, the direction? Are there any questions?
Well, you'll be seeing exactly the same equations tomorrow from Vichy.
Right. Good, good. I think it doesn't hurt to see the equations twice,
yes,
right?
That's what I meant.
Yeah. Thanks, Alex. So, but something maybe Vichy will not ask you is, who knows what Hilbert spaces are? So now, anybody? So, okay, so we have about 4 people in the audience who have seen Hilbert space before. And so maybe I need to say a little bit about Hilbert spaces, I think. That's because that's our next topic. So who knows what a vector space is? A linear space, right? Okay, good. I think more or less everyone. So in a vector space, and we're looking at vector spaces of functions, basically. We look at functions. So in a vector space, we know we can take one function and the second function, and we can compute the sum. I mean, how do we do the sum of 2 functions? We just, when we evaluate that function, we just add the function values, right? So that's how the sum of 2 functions are defined. And we can multiply a function with a number, so we get a linear space. So that's easy. So now a Hilbert space, in addition to being able to add and to multiply with scalars, we also have a scalar product. That's the key thing. So it's like a Euclidean space. So we have a scalar product, and of course, hence we also have a distance, for example, and things like that. And that's important. Now, but the difference between our standard Euclidean space, like our R3, and the Hilbert space is that the Hilbert space typically is infinite dimensional. So we have, instead of having a finite basis where we can represent everything, and compute our scalar products, we now have an orthonormal system, or a finite, or we might even not have that, but typically there exists such a thing, which is of infinite length, and we will assume so-called separable Hilbert spaces. So we have a countable orthonormal system. Countable just means that we know we have a first basis vector, a second, a third, and so on. We can count them. We can line them up. It's like Fourier Series. Has anyone ever heard of Fourier Series before here? Yes, I think everyone. Everyone. Good, good. Okay, so if you look at Fourier Series and you look at the Fourier coefficients, and look at the sum of your squared coefficients, that gives you a norm, and also basically a scalar product. It gives you a so-called L2 space, right? For example, if you look at Fourier series over the interval 0 to 2 pi, right? So that's a special example of a Hilbert space, separable Hilbert space. So if you have a problem, just think about your Fourier series. So now there's one important property we have, and this is covered by this here, the Riesz representation theorem. So now this is a little bit of mathematics. What is this about? It looks sort of bad, doesn't it? But what it is, we have an element from our Hilbert space, right? So we have our function, say. And what can we do with functions? We can compute function values. So what is actually a function value? So we take an argument, an x, and take our function and somehow combine them, and out pops a number, which is the function value, right? So which we write as for example, as f of x. So we take, so let's say H is our Hilbert space, F is from our Hilbert space, so that's, you know, our Fourier series, for example, and then we also have an X, which is from our domain X, and we get our f of x. Now, usually we're very much aware of looking at taking an x and getting a function value. Maybe what is less common and what is done here is that we say, okay, let's study how our f of x depends on f. And that's what this is about, right? That's what this is about. And so now we look at how does our function value not depend on the x? Let's fix an x. But how does it depend on our f? Well, we can see straight away it's a linear function of f, right? So if we have two functions, the sum of two functions, the function values is the sum. Or if we have a multiple, you know, I mean, by definition, it's linear. But now the most important property here is to relate this to our scalar product and to our underlying topology. And so now the big assumption we make is that this function, f of x, is continuous. But, so I can see Vishy saying, oh, are we only looking at continuous functions? The thing is, we're looking at it as continuous, not as a function of x, but as a function of f. Or, in Hilbert spaces, and it's the same thing, that our f of x is bounded in terms of our f of x, in terms of our function f. And this is what this is about. So now, and in fact, you know, the Rees, I guess the Rees, there were two brothers, Rees, and this was the, let's see, I think this was the older one. I think, I forget now which one. But sometimes they work together, Hungarians, if I remember correctly. And in 1907, and these guys, they sort of basically invented an area called functional analysis, right? Of course, with several other people. So this is one of the key results. So if you look at a continuous function, functional on a Hilbert space, so this mapping from f to f of x, so now we only look at, we assume that our x is given, and we look at this mapping from f to f of x. This is a so-called functional. A functional takes a function and computes a real number. And that's what this is. You know, it assigns a real number to an element of your Hilbert space, right? That's a functional. And so we assume it's continuous or bounded, which is the same thing here, in terms of our Hilbert space metric, in terms of our Hilbert space topology. So if we know that that's the case, then there's a unique element in our Hilbert space, which I call G phi here, such that we can actually write this phi of f as a scalar product. So now you can see, you know, the sort of the beauty of things like this here. I mean, here you have scalar products all the time, right? So in certain cases, you know, you get sort of quite natural scalar products for your functionals. But then you say, hey, well, you know, actually, all functionals are continuous, aren't they?
No.
They're not, right? They're not. See, that's the thing. So if you look at, for example, you know, if you try to have function values of L2 functions, of square integrable functions, you know, for some functions, you know, you get sort of reasonable things. But now you can have two functions which are very close to each other. So just look at the function like this here. And I think it's very important to understand these types of examples. Sorry?
When you use the fat pen.
The fat pen, yes. Yeah, sorry. Is it okay to use that board there? Now I have to find the fat pen.
It's just there.
Ah, yes. It was too obvious. I never see things which are in front of my nose. It's like in research, the mathematical research that often happens. You sit there and you can't solve a problem. It's really very hard, and you try to find this answer, and then so they say, well, it was sitting in front of my nose all the time, like this pen here. Okay. It's a bit of... So here we have this nice function here. And so now we have a function which is very close by. Maybe something which is very close to this here, but has a little blip just here. So the function value here would be very different to the function value here, right? However, if you look at the difference and you take the norm of the difference, the L2 norm of the difference here, so the squared, so this, if we call this F1 and this F2, if we look at F1 of x minus F2 of x, right, and take the square of that and integrate that over dx, depending on how narrow this thing is, this would be very small. So what happens is that two functions are very close to each other, but their function values are widely different. So that's sort of the nature of where this sort of discontinuity comes from. Yeah, Markus.
Question not regarding continuity of the function phi, but shouldn't phi be also linear? I mean,
yes, yeah, that's right.
Is that missing in the theory? Should be continuous linear function?
Yes, that's right, continuous. I just assumed, linear functionals at this stage. Yes, no. So, yeah, thanks, Markus. Good point. Yeah. So you're absolutely right. It should be linear. Okay, so why is this the case? So I'll just show you a little bit of mathematical reasoning. And I think, as I heard from lectures in the first week, Sam's lectures, some of the basis of the intuition in mathematics is geometry. So your reasoning, even in Hilbert spaces, you go back to your intuition which you have from basically 2 or 3 dimensional geometry. And that's what we can do here as well. So what we look at, so we first look at a space where our functional is 0. So we look at the null space. So here where all phi of x is 0. And we look at that. And I'll draw that here. So this is our Hilbert space, right? And this is our n of phi. And here is our 0 element in our Hilbert space, our 0 function. And so now this is a piece of information which I'll let out, but this is standard analysis, that the null space here is closed. It has to be closed. So that's an important condition. Sometimes spaces in high dimensions, finite dimensional spaces subspaces are closed, but infinite dimensional spaces don't have to be closed. And that's a problem which we face when we do regularization, because there we have to overcome this difficulty. So now we look at the space which is orthogonal to this here, the orthogonal space. So here n phi is closed, and we know that our Hilbert space is the direct sum of these two things. And which means that any element in here can be written as the sum from the null space plus the sum in here. So that's phi. That follows from the continuity and the linearity. Now also there's another important thing, that we can show that this space here, the dimension of this space, it's finite dimensional, but its actual dimension is 1 or 0. So, the simplest functional, of course, is the null functional that maps every function onto 0, right? So in that case, this here would be 0, right? Now, in the other case where this is not 0, this space is one-dimensional. And why is that? If we take any two elements here out of this orthogonal complement here, and we look at this element here, which is the value of the function, which is a number times the other one, minus this here, if we look at this, then we know that if we evaluate this phi on this here, we get phi of u1 times phi of u2 minus phi of u2 times phi of u1. So that's 0, right? So this difference here is actually in our null space. But because it's a linear combinations of element in the orthogonal complement, it's also in here. So it has to be in both, you know. And so if something is in the intersection of a space and its orthogonal complement, what can we say then?
It has to be 0.
Yes, thank you. It has to be 0. So basically it has to be orthogonal to itself, you know, and it has to be 0. Okay, so that's the key thing here. And so consequently, you know, this here has to be 0, which means that u1 and u2 are linearly dependent. Which means, of course, that we cannot get any more than one-dimensional subspace here. And the thing here is that this orthogonal complement is one-dimensional. So we take any generator out of here and normalize appropriately, then we get this G phi. So that's what this is all about. So it's really very simple, and you can see there's a simple geometric intuition behind this Riesz representation theorem, even in infinite dimensions. So we didn't assume much at all about our spaces. Okay.
This proves the uniqueness, but not the existence, your argument.
So this is
the uniqueness.
This is existence. So what I proved is existence. So I proved, you know, that there existed, right? Well, obviously, so I proved, you know, there is this n phi orthogonal, right? And this spans the whole space because this thing here is closed. I mean, the general theorem is actually that a whole space is spanned by any subspace if you take the closure of that subspace plus the orthogonal complement, right? So that's now if it's closed, you know, you have that is the same. So that means that these things exist. And here I have uniqueness down here, and I'm not going to go into this because this is sort of really very much along the same reasoning. But what I wanted to show you, you know, that even in very high dimensions we can use elementary geometric reasoning. So Hilbert spaces are nothing to be afraid of.
And so basically it's the continuity which gives you the fact that you can write the space in dot product notation.
Yes.
I mean,
yes.
you can write
yes.
the space as the...
So the continuity gives you that this space here is closed and that H is, and I have it up there, H equals n phi plus n phi, the orthogonal complement. If you didn't have continuity, you know, you would have to take the closure here. So that's difficulty, right? But here we assume continuity.
So for those who came to my lectures in the AMC summer school, this should be clear.
Okay. So I just repeat, you know, and for clarity, you know, you have to go to Vichy, and maybe get more clarity tomorrow as well. Okay, now let's see. So now we look at, so now we had this theorem by Riesz on general functionals. Now in 1950, Aronshine and Bergman looked at reproducing kernel Hilbert spaces, right? And there they looked at Hilbert spaces where the functionals which related to the function evaluation functionals, which you could call delta x of phi, so this is of f, so this is our phi from before, that they're continuous or bounded. And so we assume, so this is what this means. So this is basically our continuity, means that the function values are bounded by some constant which may depend on x times the norm in our Hilbert space. And so now by Riesz we know, okay, there is a k of x which is an element of h such that f of x is the scalar product. Now that is the reproducing kernel of our Hilbert space. So the key thing here is that functional evaluation, function values are a continuous functional of the function, of the element. So function values depend continuously on the function. So why is that, for example, important? So if you do approximation in that space, approximation you do with respect to your norm in the Hilbert space. So you say that, okay, we have a good approximation if the distance in our metric, if the norm of the error, right, is small. And then if we have a reproducing kernel Hilbert space, then we know that automatically we have a bound also for the function values of the error. If we don't have that, if we do approximation in L2, we don't have that. And there we cannot say anything about the function values, about how good, the function values are approximated by your Fourier series, for example. However, if you have a reproducing kernel Hilbert space, you can say something about the function values. So convergence in H, from that we get as consequence convergence of our function values. If we have uniform, we get even uniform convergence if we have a bound on the norm of our kernels, which is independent of x. And in this case, and I'll talk a little bit about embedding too. In this case, we have an embedding from our Hilbert space in the space C of x, the space of continuous functions where the norm is the supremum's norm. So the norm in that space is given by this thing here. So, and if we have an error, where the norm of the error, this norm here of the error is small, then we know that this function is everywhere small. The error is everywhere small. So that's a nice thing. So in that case, we have that. So why do we need all this stuff, this mathematical stuff, right? Why do we need this? We want to approximate. Remember, we want to approximate. So we want to compute approximations of our functions. And you'll see how we'll use that for that. So now there's another connection here with Green's functions. Has anyone ever heard of a Green's function? Yes, so maybe half the audience have heard of Green's functions. So Green's functions, they occur in the solution of elliptic partial differential equations, linear elliptic partial differential equations. And the nice thing about the Green's function, you can write down the solution in terms of an integral with your Green's function and your source term. So I'll show you a little bit how that works here in this case. So assume that we have two Hilbert spaces now. Two Hilbert spaces, an H0 and an H1. And that's important here. For Green's functions, we need two Hilbert spaces. Okay, so in terms of our functions, we have one Hilbert space we know about. If we have a measure, a probability distribution, we get the so-called L2 space, right? The L2 space based on that measure, where the scalar product is just the product of your functions and integrated over the measure, right? So that's an L2. So that's this one here. So this is our H0 we're interested in. And in that space, typically, our function values will not continuously depend on your functions. Yeah, it depends, but typically we don't have that case. So we need a second function space, H1, which is a subspace, and I'll only look at the case of the subspace where H1 is a subspace of H0 here, and where we have another norm. So we have another scalar product, which is different, and in that case the function values are a continuous function of our functions. And so now you could say, okay, since H1 is a subspace of H0, we could look at this very trivial mapping, which takes an element of H1, right, and says, okay, since it's in H1, it's also in H0, we'll map it onto itself as an element of H0. That's embedding. So, this mapping doesn't do very much at all. It just reinterprets it. So it reinterprets the framework around it to say that, first it was in H1, now it's in H0. And so now a consequence of our representation theorem from 1907 from Rees is that this embedding has a so-called adjoint. And that's sort of where the magic comes in a bit. What is an adjoint of a linear operator? Has anyone heard of an adjoint of a linear operator? Yes, there are a few. Has anyone heard of a transpose of a matrix? Many. I would guess about 80% of the whole audience have heard about transposes of matrices. The other ones maybe should ask the other 80%. So an adjoint of a linear operator is basically to operators what the transpose of a matrix is to matrices. And how do we formulate this here? The thing is that if we take any element G of H1, and we look at EG, which is still the same as G, with the scalar product of F in our Hilbert space H0, right, in our original space, then the adjoint is the operator which is such that this here is equal to a scalar product in our new space, in our smaller space. So there's a mapping which takes this F out of H0 and maps it onto an element in H1. Now this is not trivial. Right? This is not like E. E takes the element out of H1 and basically maps it out onto itself, and it's now interpreted as an element of H0. E star, the adjoint, is something quite different. However, it's closed and it's uniquely determined by E, and it's related by this relationship here. So we'll see how we can use this, but maybe most interestingly, we get here a characterization of our E star of F. Remember, so F is in our H0, so we define our U as E star of F. We just introduce a new notation or a new symbol U for this A star of F, and let's see if we can compute this U somehow. Right? So what we do, if we look at this here, well, we see we put this is our U, right? And this equation, of course, has to hold for all G. This has to hold for all G. So we just rewrite this equation here. So G scalar product with U in the one norm equals G. And so here I just write G instead of EG because it's basically the same. G, the scalar product of G with F in our zero norm. And these are the so-called Galerkin equations for our U, or variational equations for U. So this characterizes our U. This is also, you might not see it at at first glance, but basically this is an elliptic partial differential equation, right? Well, this is a generalization of an elliptic partial differential equation to our context. So you don't really need to know what these things are, but you need to know, that our U is characterized by these equations. And the thing is that these equations hold for all G in H1. And so, in the case of elliptic partial differential equations, we have some differential operator, T U equals F. And the solution of this equation is not always, but I guess many times, the same as the solution of this equation. This here, the solution U here, is called a weak solution of our partial differential equations. And these are the type of equations we want to solve. This is the type of things we will use. We can characterize this differently. The weak solution U also minimizes this here. And you can get from this here, you can get straight away an optimization problem. Right? And you see here, you know, this is sort of like a norm of our U squared, right? This could be maybe something like a prior, for example, right? And this here might relate to our data later on. But we'll see in more detail how these things work. Now another interesting thing is, what if we choose a special G here? What if we choose for our G just our reproducing kernel Kx? Well, if we put Kx in here, we get Kx, scalar product with U, which is just U of x. So U of x equals this here. So we see that actually the function value of U is the scalar product of K of x with f in our zero norm. So now I'll just write this down if we have an L2 norm, what this looks like. And you'll see straight away that this is actually not all unfamiliar at all. U of x equals, and remember our H0 was an L2 with measure P. So the scalar product here is, you know, just the L2 scalar product. So this is equals, it's just an integral over our x, K of x of y, f of y, p of y, dy, or you can write, you know, dp of y, or whatever you want to, which way you want to write it. So the solution can be of this variational problem or of this minimization problem can be written down straight away. And this K of x, our kernel, is actually the Green's function which belongs to this variational problem. Now, in the literature, and also in the machine learning literature, you might find that, you know, other Green's functions, being like the square root of the kernel, things like that. So that's possible too, but the reason why I get that there is because they look at different operators than the ones here. And I like to come from, you know, our variational problem, and that's why we get these, actually that the kernel is equal to the Green's function. I don't know, maybe, are you going to say something different, Vichy, tomorrow? No? No, okay.
I don't go into Green's function.
Okay. This is just to show you that the stuff from PDs is applicable here. Okay, so now kernels and Gaussian processes. You know, this is something which Vichy will talk about a lot, I'm sure. You know, so that we have random variables U of xi with expectation 0 and covariances like so. And well, this is actually the famous result by Waber and Kildorf on an equivalence of two Hilbert spaces. So now the thing is that why would you want an equivalence? So it's an equivalence of Hilbert spaces defined with random variable, and after that I'll make a break, and our reproducing kernel Hilbert space. So they look at these Gaussian random variables U of xi, and they look at linear combinations of these, because these linear combinations relate to, for example, estimators, which we'll use. And they map these random variables onto our kernels. So you can say, okay, we'll map our random variable U of x onto our kernel. And you see that you could define a scalar product in these random variables like this here. Our expectation of U of x is 0. So this here defines a scalar product on our random variables just by taking the expectation of the product of these two. Of course, by definition, this is the kernel. In our reproducing kernel Hilbert space, this here was actually the scalar product of k of xi with k of xj. So, this mapping maps random variables onto kernels and linear combinations of random variables onto linear combinations of kernels, which is simple. And then at the end, what you need to do a sort of a closure over your metric on both sides. And you see that the space of functions which are approximated by linear combinations of kernel functions is isomorph, which means it's basically the same as our space of created by our random variables u of xi. So I think this is so we're still leading up to the sparse grids. I hope we'll get to the sparse grids today sometime. Huh? But we'll have a quick break. Huh? What do we have for 5-10 minutes?
Yeah, 5 minutes.
5 minutes. Okay, thank you.